Hello, dear students. So this is in fact my first virtual class, in fact, without the students. So I don't know how much it would be successful, but I will give my try. We have been trying a lot of online sessions during the last 1 month. So what I felt was that the lectures were in fact very lengthy, and when I tried to capture those recorded videos, it was difficult to download them and send it over to you. And even though I was sending it to you, it was almost extended up to 2 hours, most of the sessions, because there were discussions also in between. So I think, I thought this would be a better way to reduce each session and try to, if I try to upload it in YouTube, you might be able to download it as and when required, depending upon the assignments in fact given to you. And I hope, let us see how far it is going to go. So, in the last, this is in fact the sixth lecture on discrete time systems. And in the last sessions, what we had seen was modeling of discrete time systems. And we derived the pulse transfer functions, we modeled the sampler, we modeled the zero order hold, and we found out how to form the transfer function of closed loop systems, different types of closed loop systems. Okay, now our next step is analysis of how do we analyze a discrete time system, whether the given system is stable or not. That is what we are going to do. So what I have thought is I have divided the whole session into, I've divided it into three pieces, so that I will start with the stability part. In fact, for going to the stability, we should have a little bit of knowledge on the S and Z plane relationship. That is what I'm going to cover in the lecture. First lecture, this YouTube lecture. And the second part would be on how to find out whether a system is stable. For that, we will see the jury's stability criterion, which is in fact similar, almost similar to that of the Ruth criterion that you have studied for the continuous time systems. And the last one would be on bilinear transformation, a little bit of motivation on why we need to study bilinear transformations. And then we will see how to find the stability using after doing the bilinear transformation. So this will be the three sessions that we will cover for the stability of discrete time systems. And then there would be one more topic which is on state space analysis of introduction to state space for discrete time systems. Okay, that is would be only one lecture. In fact. So now let us start with the stability of discrete time systems. Okay. So, before starting that, let me ask you one or two questions based on which you all know on continuous time systems. For any way, we all know in the continuous time domain, we represent the transfer function of a system in the Laplace domain, right? We write it in h of s in the Laplace domain. H of s, let it be s raised to 5 plus b1 s raised to 4 plus b2 s cubed plus b3 s squared plus b2s plus this is b4 plus b5 divided by like I would avoid this part so that okay, s raised to 6 plus a1 s raised to 5 plus a2 s raised to 4 plus etc up to a6, right? This is how we represent a continuous time transfer function. Okay, so from the continuous time transfer function, how will you assess the stability of the system? That is a question. So we all know like the roots of the denominator of a continuous time transfer function in fact gives the poles of the system. So the roots of this in fact gives the poles of the system, right? So if we know the poles of a continuous time system, then we can easily speak about the stability of the system. Okay, so if I am drawing, this is the sigma j omega plane, sigma j omega axis of the S plane. So we can speak about the stability of the system. So when can we say that a system is stable? So we can say that the system is stable when all the poles of the system are on the left of the imaginary axis. I think all of you know about this, right? So when can we say that the system is unstable? So in the case of instability, we can say that if there is any pole on the right of the imaginary axis, or if there are multiple poles on the imaginary axis, if there are multiple poles on the imaginary axis, then that means that the system is unstable. Here it becomes unstable. This is unstable point. And the third one is marginal stability. Marginal stability. So when do we say that a system is marginally stable? When can we say that? So we say that a system is marginally stable when there are simple poles on the imaginary axis and all the other poles are on the left of the imaginary axis. Okay, then all these conditions are not new for you. This is thorough for you. These terms are thorough for you. You might be knowing all these things. Now we are going to from the S plane to the Z plane. Now when we deal with discrete time systems, we are in the Z plane. In the Z plane, we also have the sigma j omega axis here, j omega axis, and we also know the Z transfer function here, right? H of Z. So h of Z also can be written in a similar form as that of a numerator polynomial in Z to a denominator polynomial in Z. So here also I can write Z raised to 5 plus b1 Z raised to 4 plus etc. up to Z b5 divided by Z raised to 6 plus a1 Z raised to 5 plus etc. a6, something, some kind of a transfer function. So how do we speak about the transfer functions or about the stability of the system? How do we assess the stability of a discrete time system? So when so the question is there a way that we can assess the stability of the discrete time systems in the similar way looking at the poles of the discrete time system? In fact, here also the poles are the roots of the denominator polynomial. Okay, so this is the denominator polynomial. Here also the roots would be the denominator polynomial. Is there a way to assess the stability of the system? That means assess these three terms. That means we should know when the system is stable, when the system is unstable, and when the system is marginally stable. So now if we are able to map the left of the imaginary axis of the S plane onto the Z plane, if it is possible to map the left of the imaginary axis onto the Z plane, then what can we say? What can we say about the system? What can we say about the system? That means we can say that the system is stable. So if we are mapping the left of the imaginary axis to some region like this, right? Some region like this. And we say that this is the area where the left has been mapped to. Then we can say that if all the poles of the system are inside this region, then the system is stable. Okay, that is what we are going to do. For this, we know that this transformation from the transformation from the S plane to the Z plane can be done using the transformation Z is equal to e raised to st. That is what we are going to do today and see what are the conditions on the Z plane for the system to be stable, unstable, and marginally stable. Okay, so now we'll go to that. So for that, first we will consider the S plane. For this first, what we are going to do is mapping. This is mapping. So this is the S plane. I'll draw it here. Okay, this is the S plane. This is the sigma j omega axis, and this is the corresponding Z plane. This is the corresponding Z plane. This is in fact the S plane. Here also I will write it as sigma j omega. So we know the transformation here. So I will write down the transformations here. Z equal to e raised to st. And here t is the sampling period, right? We all know t is the sampling period. Now we know what is the sampling frequency. Sampling frequency omega s can be written as 2 pi by t. And also what is this s? Any point s on the S plane will be mapped onto some other point on the Z plane. So this S is a function of a real part of the S plane and the imaginary part of the S plane. So I can write here S is equal to S is sigma plus or minus j omega. Right, S is sigma plus or minus j omega. Right. So now what is this? How are we going to transfer it to the system? For that, what we will do is, so I will also write one more relation here. Z is equal to e raised to sigma t into e raised to plus or minus j omega t, depending upon where this omega is, right? It is on the positive imaginary axis or on the negative imaginary axis, right? So I'm going to divide the whole S plane into strips. So this is in fact a strip here. This is one strip. This is another strip. So I have divided it into strips of equal lengths. This is one strip, this is another strip, this is also another strip. This point is 0, okay? The center point is 0. So, and I have divided it into strips of equal lengths. This width is omega s. This width is also omega s. And this width is in fact also omega s, even though it is looking a little bit bigger than the other two. It is also omega s in fact. Okay, now we will write another relation here. So this is omega axis, j omega axis. This here omega is varying from 0 to plus infinity, and here omega is varying from 0 to minus j infinity, right? So I am going to take these strips of width omega s. Of width omega s means that this varies from 0 to j omega s by 2, and here 0 to minus j omega s by 2. So what is omega s by 2? It is pi by t, right? So this varies from minus j pi by t to, one second, standard I want. This varies from minus j pi by t to 0 to plus j pi by t. Okay, is that correct? Now, what is this? From here to this, I am having 3 j omega s, right? This is j omega s by 2. I will write also those values also. This is 0. This is j omega s by 2. This is minus j omega s by 2. This becomes plus 3j omega s by 2 minus 3j omega s by 2. Okay, fine. So this becomes plus 3 pi by t. So this also becomes, here also I will write plus 3 pi by t. Okay, this j is there. Here it is minus j 3 pi by t. Okay, only now what we have to think is about the strips only. We are going to we are going to transfer or transform the strips or map the strips onto the z plane. Okay, using the transformation that we know E is equal to z is equal to e raised to st. For that, first we will consider the strip varying from minus j pi by t to plus j pi by t. I am going to consider this strip, the strip which is going from minus j pi by 2 to plus j pi by 2. This is the yellow line. Okay. So I have the strip here. So case 1. So okay, since it is in yellow color, I will write it in yellow. Here, this is case 1. Case 1. So omega varies from minus j pi by t to plus, in between there is a 0 here, to plus j pi by t. Okay, so for in order to get 1 or 2 points, I am going to put one more value here in between. Here I'm going to put one more value here and here. Take one more value of omega in between 0 and minus j pi by 2 and 0 and plus j pi by 2. So this would be minus j pi by 2t, and here it would be plus j pi by 2t. Okay, so now we will see where does this transform to, right? Now we have to transform this line onto the j omega, onto the z plane. So we will use the relation E is equal to z is equal to e raised to st, right? Here sigma equal to 0. Here in this case, sigma equal to 0, right? Sigma equal to 0. So this implies that z is equal to e raised to j omega t. So this becomes, it maps onto where? E raised to minus j pi, e raised to minus j pi by 2, e raised to 0, e raised to j pi by 2, e raised to plus j pi. That means this whole thing is mapping onto magnitude. I am going to write it in terms of magnitude of this and the angle of this. 1 angle omega t. So this omega t is varying from pi to minus pi to plus pi. Omega t is varying from minus pi going to minus pi by 2, then 0, plus pi by 2, and then pi. That means with a magnitude of 1. That means I am having what? What am I having? So I have a magnitude of 1 Okay, I will not take this. Take a stroke. So it starts from here minus pi with a magnitude of 1, then goes to minus pi by 2, then goes to 0, then goes to plus pi by 2, and this comes to 1. That means it is going in the anti-clockwise direction with a magnitude of 1. That means it is in fact a unit circle. Right, it is in fact a unit circle starting from minus pi to 0, then again to plus pi. And this minus 1 point is in fact this point. I'll call this as A and this point as B. It starts from A, goes to B. This is A, this point is A. It starts from A, it goes to B. This point is B. Okay. So that means this part of the imaginary axis is in fact the unit circle. This unit circle. In fact, this is the contour part. Okay. Now we will see. Now we will go to the other parts of the strip. So I will go using this red color. So we will see this part. We will see the point B. We know that point B is here, right? Point B is here. Point A is here. This point only, same point. Since I didn't have space to write here, I have written here. So this is point B. So now I'm going from point B, which is at plus j pi t. I'm going to here. When I move along this line, the omega is constant, but what is varying? Sigma is varying, right? Sigma is varying. So sigma is less than 0, right? Sigma is less than 0. And if I move from B to the right, what happens? Sigma is greater than 0. Sigma is increasing. Here sigma is decreasing and it is going to minus infinity. Here sigma is increasing and it is going to plus infinity. So how will it look like? So I am going to take the red part, case 2. Case 2. So it is going from B to minus infinity and B to plus infinity. B to minus infinity means sigma is less than 0. B to plus infinity means sigma is greater than 0. So that means when sigma is less than 0, what will be e raised to what will be z? Z is equal to, we know, e raised to sigma t, e raised to j omega t. We know what is e raised to j omega t here. E raised to j omega t is this point, right? This is the B point. Sorry, this is in fact the point B, right? This is the point B. This is point B and this is point E. Okay, at this point, what is the value? The value is minus 1. At A also, it is minus 1. Okay, so we have e raised to sigma t e raised to j pi. So e raised to j pi is 1. So it will be e raised to sigma t into, so not plus 1, it is minus 1 into minus 1. So when sigma is less than 0, what is happening? Minus, the magnitude of minus 1 is decreasing. That means the magnitude of minus 1 is decreasing. So that means it is going from B towards 0. The magnitude of minus 1 is decreasing. The magnitude is decreasing, and when sigma reaches infinity, when sigma goes to infinity, what happens? This term goes to 0. So it starts from B as sigma decreases and then it will hit 0 when sigma equal to minus infinity, right? So this is sigma less than 0. condition. Sigma less than 0 condition, it goes from B and goes and hits 0. Now we will see sigma greater than 0. What will happen when sigma is greater than 0? Z is equal to e raised to sigma t e raised to j pi e raised to sigma t. This term is increasing. Here this term is decreasing because sigma is negative into minus 1. So the magnitude here is increasing from 1. Minus 1 and increasing. So from point B, this point is going towards the left of the unit circle when sigma is greater than 0. And that means when the line towards the right of the imaginary axis on the z plane, where it will be from minus 1, it will go to minus infinity. It is going to the outward of the unit circle. And the left of the imaginary axis, it is going to the inside of the imaginary axis. That is very important. Similarly, if we go and take the point here at point A and we walk towards minus infinity, from point A we are going in this direction, we are walking towards minus infinity. That means we are decreasing. The same equations will be applicable here. Only difference is here it will be minus j pi. Minus j pi will also be equal to minus 1. Okay, so here case 2 is also applicable from A to minus infinity and A to plus infinity. In both cases here sigma is greater than 0, A is going to minus infinity. So I will write here plus or minus j pi. Plus or minus j pi. This is plus or minus. So this is not plus or minus, it is minus 1 itself. Plus or minus j pi, whatever it is, this is minus 1. That means from A, it is, when sigma is lesser than 0, it is again going to decrease the magnitude, right? Minus 1 magnitude is, the magnitude of minus 1 is decreasing and it goes and hits 0 as sigma goes to minus infinity. And from A, when we walk towards the right of the imaginary axis, sigma is increasing and going to plus infinity. That means we will have to walk away from the imaginary axis from A. So this point also, this part is, we are walking away from the imaginary axis. This part is, we are walking into the unit circle. Okay, to the inside of the unit circle. I think I said something wrong here. Okay, I think you would have understood that. Now the only part remaining here is this line, right? The white lines here. So the white lines I will do with this blue color here. So I have the 0 point here. So from the 0 point, I am going to walk away to minus infinity. So where is the 0 point on the z axis? So I will call it as C, the center point. And this point is in fact here, right? This is C. This is C. That is e raised to 0 is 1. This is the point C. So I am walking from C to the left of the imaginary axis, sigma less than 0. Then if I walk from C to the right of the imaginary axis, there what happens, sigma will be greater than 0. So I have the case 3 here. Case 3 here. C to minus infinity, right? Sigma less than 0 and C to plus infinity. That means here I will write it near this so that confusion will be there. This is sigma less than 0. This is sigma greater than 0. For this, how will we get the mapping? The similar way, we have z is equal to e raised to sigma t. That is, for sigma greater than 0, we have Z is equal to e raised to sigma t, that is e raised to sigma t into e raised to j0, right? So that is e raised to sigma t into 1. Here, when sigma is less than 0, the whole magnitude is decreasing. That means the point C is going to the inside of the unit circle. The magnitude is decreasing. That means 1 is decreasing, and where will it go maximum up to? It will start from C, and when sigma is equal to minus infinity, the maximum value it will reach would be 0. It will start from here and it will hit this 0 point, right? So it starts from here and hits here when sigma is less than 0. Now when sigma is greater than 0, I think this is less than 0, I wrote it wrong, less than 0. When sigma is greater than 0, z is equal to e raised to sigma t into e raised to j0. Sigma is greater than 0. What happens? E raised to sigma t into 1. This term will be increasing. This term will be increasing to infinity, right? This term will be increasing to infinity. That means it is going outward from C. That means it is going away from the unit circle when sigma is greater than C. Okay, so that is what we have to see. Now we have got all the portions here, right? When we go through this, all the lines over here, that means when we start from this point, from A to C to B, we are going to infinity, and from infinity if we come here and come back here, everywhere. So I will take this small strip. I go from C to infinity, then come back here, and if I come through this point back to C, we'll see where it is going back. So from C, it goes to B. Then if I take sigma less than 0, it is taking this path. Okay, it has reached 0, and here at infinity, it reaches this line, comes to this line, and then it follows this path and comes back to 0. So it is the top part of this circle. So in between, all these points will definitely be mapped to the inside of this semicircle. So I can draw it very clearly that the inside of this part will be easily mapped. We can see that it has easily mapped to the inside of this semicircle, right? And what about this part? Similarly, this part will be mapped onto the inside of this semicircle, this part of the semicircle. So we can say that the left of this strip, that means the left of the imaginary axis of this strip, is mapped onto the inside of the unit circle. So what happens to this part? What happens to this part? What happens to that part? That part is clear. This part, what happens? The top portion, where will it be mapped to? Top portion, we know this, we have this line, and this line. The top portion will be mapped here to the outside of the imaginary axis, and the bottom portion of this part will be mapped to the outside of this unit circle, this part of the unit circle. So what can we conclude from this? What is the conclusion out of this? So if we consider this strip, that means the red strip, we can say that the left of the imaginary axis of the left strip has been mapped onto the inside of the imaginary axis, and the right of the red strip has been mapped onto the outside of the unit circle. Okay, now what about the other strips? Other strips. So here we are going from, if we take the top strip, we are going from plus j pi by t to plus 3 pi by t. That means it is equivalent to plus minus j pi by t to plus 3 pi by 2. So that means this cycle is being repeated. The whole thing is being repeated. That means it is again taking 360 rotation. That means it is starting from -1, going to -90, 0, plus 90, and then again going back to plus 180, right? This is what is happening if you move from this point to this point again. Similarly, if you move from this point to this point, the same thing is being repeated. So we can in fact map each strip onto the left of each strip onto the inside of the unit circle and the right of each strip onto the outside of the unit circle. Okay, effectively, in effect, we can say that the whole of the left of the imaginary axis is mapped onto the inside of the unit circle, and the whole of the right of the imaginary axis is mapped to the outside of the imaginary axis, right? Is that correct? Okay. Now we will go to the next slide and we will draw the final part. Okay, so this is the S plane, sigma, j omega. This is the Z plane. So here, similarly, I will draw with strips only because I want to explain one more condition here. So I will mark the previous points also here. This is B. This is A. And this is C. Let me mark this as D. Okay. Now I'm going to, so we know that the left of the imaginary axis will completely be mapped onto the inside of the, so this whole part, we can say the whole part is mapped onto the inside of the, okay, inside of the unit circle. It's completely mapped to the inside of the unit circle. Okay, so that is what is happening here. It is completely mapped. But now if I'm going to consider 2 points here. This is 1 point. I'll take a different color here. This is 1 point here, and this is one pole. Like these are the poles, 2 poles. I'm considering 2 poles on the top of these two strips. We know that B is this point, B is this point, and similarly D is also the same point. D is also the same point. B and D are the same points here now. So let this be equal to -2. Let this be equal to -2. This is equal to j pi by t, and this is equal to j 3 pi by t. Okay, this is equal to j pi by t and this is equal to j 3 pi by t. So where will these 2 points be mapped onto inside the imaginary axis? Right. So we will just see where it is going to be mapped. So I can write here z is equal to e raised to st. So here I have 2s, s1 is equal to -2 plus j pi by t, and s2 is -2 plus j 3 pi by t. Okay, so I can write s1 maps onto z1 equal to e raised to -2 plus j pi by t into t. This is equal to e raised to -2t into e raised to j pi. Okay, that will be equal to minus 1 into e raised to minus 2t. So what about S2? S2 is this e raised to minus 2 plus j 3 pi by t into t. So here we can say this also will be equal to e raised to minus 2t into e raised to j 3 pi. This will also be equal to minus 1 into e raised to minus 2t. So what does this say? We can say that the two different poles have been mapped onto the same point. So this is somewhere here, I don't know where it is, have been mapped onto the same point on the z plane. So we don't have a distinction here regarding where these poles are, like which pole has been placed here. So we are having two poles like this. Both the poles will be placed on the same point or mapped onto the same point on the z plane. Okay, using this transformation z is equal to e raised to st. Okay, that is one conclusion out of this mapping. And then we will also see like which is like just for your information, like where are the zeta lines, where are the zeta lines going to be placed here. Okay, so that also we will see. This is the sigma j omega plane. So this is the z plane I will write here. So that is enough for you. So I will draw the strips here. This is one strip, this is another strip, this is the first strip, this is the second strip. In fact, here only we require only one strip, but anyway, for completion, I'll draw all the strips. So I have the mapping like onto the mapping from the S plane to the Z plane. Okay, this circle is in fact smaller, but it is fine. Okay, 1 second, I'll just cut it and then draw it again. Has been mapped onto the Z plane. Okay, so now let me see like what happens. We know that this line, this is sigma j omega, right? Sigma j omega line. Okay, so this line, we know this is zeta equal to 1 line. If there are poles on this, on the left of the imaginary axis, we can say that this is a zeta equal to 1 line. This line we know this is zeta equal to 0 line. That is the undamped case. This is a critically damped case. Now we can see where is the zeta equal to 1 line here. Zeta equal to 1 line here is this part, right? So I will draw this. Zeta equal to 1 line is this part. This part. Now, zeta equal to 0 line. Where is zeta equal to 0 line? This is the imaginary axis, right? This is the imaginary axis. Zeta equal to 0 line is like, in fact, I will draw this is the zeta equal to 0 line. Okay, that is already, that color is there. So this is the zeta equal to 0 line. Where is it? Zeta equal to 0 line. Zeta equal to 0 line is in fact the unit circle itself, right? This is the zeta equal to 0 line. Zeta equal to 0 line. I'm only drawing one part of it, this side. So in fact, it will be the whole of the z. This is zeta equal to 0 line. So this is zeta equal to 0 line, and this is zeta equal to 1 line. Zeta equal to 1 line. So now I'm going to draw some zeta equal to zero point 0.8, zeta equal to 0.8. 0.8 means this is going to infinity and it will meet somewhere at infinity on this line. And this is zeta is equal to zero point 0.3 or something. I'll draw here. Zeta equal to zero point 0.3. This is constant zeta lines. This blue are constant zeta lines. So where will these lines be mapped to? We know this is zeta equal to 1 line. This is zeta equal to 0 line. Right? Zeta equal to 0 line. So where will this zeta is equal to 0.8 line go from? That means 0.8 is going from the C point to the infinity, which will touch this red line. Infinity which will touch this red line. This red line at infinity is this point, right? The red line at infinity to the left of this is this point, the 0 point. So this C is here. C is here. It will not go to this line, right? It will not go to this line. It is far away from this line. This 0.8 is far away from this line. So but it has to reach here. It cannot come through this part. It cannot come through this part because this part is, I think I did a mistake. Okay. This zeta equal to 1 line is this line. Okay. I did a mistake over here. In fact, okay, I did a mistake over here. This part is good. This is in fact, okay. This is, okay. This is actually this line. Zeta equal to line 1 line is this part. This is the zeta equal to 1 line. I hope I had discussed in the other class. Other slide, this is zeta equal to 1 line. Zeta equal to 1 line. And this red line is a line which is here. This is a red line, dotted red line. I will draw it here. This point is P and this point is a infinity point here. Infinity here. Sigma is equal to minus infinity point here. Okay, now it starts from C. If it has to go to infinity and touch here, that means this zeta is equal to 0.8 line would be something like this, right? It starts from C and I have drawn it a bigger one. Starts from C because it will not touch the zeta equal to 1 line or zeta equal to 0 line, but it has to go here. So that means it will take some route and come somewhere near this 0. It will not touch 0 because it is somewhere reaching 0. So it will touch somewhere here. So it will be something like this. Okay, this is zeta equal to 0.8. And what about zeta is equal to 0.3? This zeta equal to 0.3 is very close to this light blue line, right? Sky blue line. So that means zeta is equal to 0.3 is very close to that and it is trying to reach this red line. This red line here means red line B. That means it is almost very near to the B point in this red line. That means zeta equal to 0.3 starts from C and passes very near through this B point. So that means it has to be somewhere very near to the B point, but it will not touch this blue line also. So this has to go somewhere like this here. So this would be zeta is equal to 0.3. So this is how the constant zeta lines are being mapped onto the Z plane. So this is also I thought of discussing here, but so just for your information. So when I do this transformation of the zeta lines using Z is equal to e raised to st, we can see that these lines are being transformed in this form. So in between we will have all those zetas here. It will come like this. So all those zetas will be placed in between here. All those zeta lines will be placed in between these parts. So that is why here if we have n number of zeta lines, it will be placed onto the z plane in this form. Okay. So this is how mapping is done in the from the S plane to the Z plane. So now we will conclude the mapping part with the last discussion on S plane and Z plane. So we have, this is the Z plane and this is the S plane. This is sigma, this is j omega, this is sigma and this is j omega. So I have all the things, all the left of the imaginary axis has been mapped onto the inside of the unit circle, and the imaginary axis have been mapped onto the unit circle, and the right of the imaginary axis is mapped onto the outside of the unit circle. Right is mapped onto the outside of the unit circle. So what is the conclusion from this? So what can you conclude from this? So we can conclude, what can we conclude about the stability of the system? We can write down that for the system to be stable, what should be? All the poles of, all the poles of H of Z should be to the inside of the unit circle. And what about unstable condition? The system is unstable if there are any pole there, or if there is any pole, there is any pole on the outside of the unit circle, outside of the, I can write it here, unit circle, or I can write, or one more condition I can write here, or what is that? Or if there are multiple poles on the unit circle. Okay, what does the second condition say? The system, the first condition says that the system is stable if all the poles are on the inside of the unit circle. That means the yellow term. And the second condition says that the system is unstable if there is any pole, if there are any poles on the outside of the unit circle, or if there are multiple poles on the unit circle. Multiple poles are found on the unit circle, then the system is unstable. That means multiple poles on the unit circle will be mapped only because if there are multiple poles on the j omega axis. Okay, if there are multiple poles on the j omega axis which will be mapped onto the unit circle. Okay, so now the third condition we can write here is marginal stability. Stability. What is marginal stability? The system is marginally stable if there are simple poles. That means poles with multiplicity 1 on the unit circle, and all the other poles are on the left, no, sorry, are to the inside of the unit circle. Okay. So this is the final conclusion of S plane to Z plane mapping and stability condition of the Z plane. In the Z plane, that means the system is stable if all the poles of HZ are to the inside of the imaginary axis, are to the inside of the unit circle. It is unstable if there is any pole to the outside of the unit circle, or if there are multiple poles on the unit circle. And the last condition is marginal stability if there are symbol poles on the unit circle and all the other poles. For example, if there are 5 poles for the system, if we find symbol poles on the unit circle, that means which are having multiplicity 1, symbol poles on the unit circle, and all the other poles are to the inside of the unit circle, then the system is said to be marginally stable. Okay. So with this, we can end the session, and in the next class we will see how to, given a transfer function, how to determine the stability of the system. So if we are having a transfer function here, this is a transfer function. In this case, if the transfer function here we are having the order as 6, it is difficult to factorize this and see where the poles are placed. For a second order system, it is easy to factorize it, and even for a third order system, it is fine. But as the order increases, it is difficult to analyze where the poles are or factorize the system. So we have the jury stability criterion, which is similar to that of the room stability criterion to determine the stability of discrete time systems. Okay, so we will have that in the next session. Okay, thank you. Thanks for listening. Okay, let me try to switch it off.